right, we're going to be looking at practice problems now. And so we have quite a few practice problem slides that we're going to be looking at here. So hopefully these are helpful to you to understand what's going on. All right, so first we have this parallel interconnection of systems. And here are my systems. So here's A1, B1, C1, A2, B2, C2, and D2. I can now use the form that I have already derived and plug these A1, B1, C1, D1, and so forth into and obtain the state model. And this is the state model that I get. So notice it's block diagonal. And so here's my A matrix, B matrix, C matrix, and D matrix. And that's the form we get. So this is an example of how to take a system like this and create an overall state model. Now I have these lines in here. This is just to show you where the matrices went. The real matrix doesn't really have those lines. Okay, those lines are just there just to kind of help us see. So those are called partitioning lines, and they're not really there. They're just kind of there to help you see where the pieces go. So, all right, next example. We're given the state model, and we're told that the input u of t is the integral of some signal v of t. That is, u of t is the integral from 0 to t, v of tau, d tau. We're asked to find the overall state model with the new input v. So notice that input v is coming in, it's getting integrated, and then it comes in here, and it forms the system. So we're asked to find the overall state model with the new input v of t. Okay, since this input u of t is the integral of the signal, we can differentiate this equation. If I differentiate that equation, I get this equation, u dot is equal to v of t. And now I have a first derivative here, which means I have a state variable associated with this. And so in this case, the state equation for this new state, v dot is equal to 0 times x plus 0 times u plus identity times v, or 1 times v, depending on the dimension of v. And so we thus have this state that I can define x2 as u, x2 dot then is u dot, and so I can put it in this form. And so I can form the overall state model this way. So x1 is equal to x1 dot is equal to a1 x1 b1 b times u, 0 times v. Okay, it's not a function of v. U dot then is a function of v, but it's not a function of x1 or u. And y is a function of x1 but not of u, and not of v. Okay, so how does this relate to what we were looking at before when we looked at interconnection of systems? This actually defines a state model for this system, for this first system that feeds into the second system. So, or rather for this system that feeds into the original system, x1. And if I look at the state model for this equation, I have u dot is equal to 0 times x plus 0 times u plus I times v. So that's actually a state equation associated with this equation. That equation then can be used in a series interconnection and plugged in that way. So the 0 here comes from the fact that u dot is not a function of itself. Okay? And here's the I times v. Okay, so this is actually that series interconnection when I have this as the second state equation. Okay, so that's how it relates. All right, suppose now we're given this state model Oh, anyway, here, so for these matrices now, I can plug them in, and here's the state model that I get. So notice I've taken the partition lines away, and this is what we get for our state model. So this is the state model for that system that I was working with. All right, now we're given this state model. Notice I have two inputs, 2 columns in the B matrix, and a single output, 2 columns in the D matrix. And I'm asked to find the conjugate of G and the pseudo-inverse of G. Okay, so the conjugate of G, this becomes negative of the transpose. This becomes C transpose. This becomes B transpose, and this becomes D transpose. So this is what happens. Notice I use different variable names here because we now have a different input. So in this case, I had 2 inputs, 1 output. When I do this conjugate system, I have 1 input and 2 outputs. So now that gives me 2 rows here. Okay. Now with the pseudo-inverse, I first noticed that the pseudo-inverse of D, of our D matrix, is D transpose. So that simplifies things a lot. If I go back and look at the form for the pseudo-inverse, and then I just plug in all the matrices stuff, and I get these 4 matrices. Okay, and so if you go through and you multiply these 2 transfer functions together, you should get the identity matrix. In this case, it's going to be just the number 1. Here we have a transfer function, and actually I showed this in the last lecture as well. I can get this form of the transfer function, and again, this form of the transfer function is obtained by taking each of the transfer functions, each of the individual transfer functions, and obtaining a state model for that transfer function. Okay, and then combining all of those state models together into a block diagram. So in which case I have some in series and some in parallel, and so all of that combines to give this. That's where this guy came from. This is the Gilbert realization that we get from that. All right, so here I have a transfer function matrix. I can show now, if I take this transformation matrix and multiply on the left by a unimodular matrix. So this is a particular unimodular matrix. Okay, and this matrix is defined, so this first row is defined so that I get a 1 here, so instead of a 4. This row is defined so that it does the kind of like a row echelon kind of form. It basically makes that term 0. Okay, and so that's when I multiply this matrix now by this, I get this. So an upper triangular matrix. I take this upper triangular matrix, multiply on the right by this unimodular matrix. Now it's easy to see this is a unimodular matrix because the diagonal, it's a triangular matrix, and the diagonal matrix, diagonal elements are all constant. So the diagonal elements are constants. This is a triangular matrix. Okay, it's upper triangular. This is lower triangular, and so it's a unimodular matrix, and it is a polynomial matrix because it has this polynomial term. This has a polynomial term. When I multiply these 2 guys together, now why do I choose it? This one basically keeps that column the same. Now this column is used so that when I multiply this times these 2, I get as, well, actually this times this row times that column gives me 0 here. So that's how this column is chosen. And I chose this guy to be 1 to keep it simple. as opposed to some other number like 8. I could multiply this column by 8 and I would still get 0 here. So anyway, this is what I get when I multiply this matrix by this unimodular matrix. And so what we've shown here is we can take, in this case, a square matrix. It doesn't have to be square, but a square matrix and make it into a diagonal matrix. If it's not square, obviously it can't be a diagonal matrix exactly. Okay, so that's what we've done here. All right, now how do we take this transfer function matrix and make it into a matrix fraction description? So as I mentioned, one way is to choose D such that each diagonal element is the least common denominator of that column. So if I look at this first column, the common denominator is going to be s plus 1 over s plus 2. Okay, so if I were to want to add these two fractions together, I would have to have that as my common denominator. So that's the least common denominator, s plus 1, s plus 2. This column has also the same common denominator, s plus 1, s plus 2. Here, I switched them, but it's the same. So now when I multiply this matrix on the right of this, I get this quantity. So this is my n of s, and now I have n of s and d of s. And this, we can see, is a polynomial matrix, and so we're good. We have a matrix fraction description. How would we find a matrix fraction description of this system? Well, we first seek a basis for the null space of this matrix. So here's the matrix, Si minus A inverse minus B. Okay, so we're looking for the null space of this. So we can go through in MATLAB and do this by using the command null, and it would give us the null space. And here is a basis. Now when MATLAB gives you a basis, it generally makes these bottom guys 1, but what that does is it creates fractions in all of these terms, and so to get rid of the fractions, I multiply through by this quantity, and we get polynomials. Okay, so this is a basis for the null space of this matrix. If I take this matrix, multiply by this matrix, I will get 0. Okay, so that is the basis. And so if I take now this portion down here to be d of s, and this portion up here to be x of s, I can partition it that way. So how do I know how much of this is x and how much of this is d? Well, the way you find out is that d needs to be square. So I just choose the square portion down here and let x be whatever's left over up here. Okay. Now we take x and d. So d we know, and that's going to be our denominator. In fact, this is the same denominator that we had last time. And I multiply c times x, and I get this quantity. And d is this quantity. And what we get then is exactly the same as what we got in the previous example. Here, we get the exact same matrices because the state model that I chose just happens to have this transfer function. Tricky. Well, it makes for keeping things tidy that way. So, these are some examples. I hope they're helpful to you. Thanks for watching.